if x is a continuous random variable and we are given its CDF function big F of x, then to find PDF from CDF, we have to find first derivative of CDF function. Now, in a case when we are working with bivariate joint distributions, to find joint PDF from joint CDF of two random variables x and y, then we have to find it in a similar fashion to the case when we're working with single random variable. However, this time, since we have big F of x is a function of two variables, then we have to find second partial derivative of that CDF function. So to find joint CDF from joint PDF function from a joint CDF function, we had to take second partial derivative of big F of xy. So let's take a look at the following problem. Here we have to find a joint PDF of random variables x and y, and CDF is given as follows here. So we have to find second partial derivative of CDF, joint CDF function. First, we take partial derivative d dy. Holding x as constant, we'll get 2 plus 2y. Now we are taking partial derivative d dx. Now holding y constant, we'll get 2x over 3 multiplied by, let's factor out 2, 1 plus y. So 4 over 3 x 1 plus y is a joint PDF function which we derived from joint CDF function. Now that we have studied bivariate distributions, we can easily extend the concepts applied to the cases when we had two random variables to the cases when we'll be working with more than two random variables. A list of random variables, let's call them x1 through xn, are called random vector. And instead of listing those random variables every time, we can use a convenient standard vector notation, big X, that should be in bold. Now, similar to the cases when we were working with two random variables, we started by looking at a PDF of discrete random variables. So in a multivariate case, probability is that random variable x1 is equal to small x1, big x2 is equal to small x2, and so on. Random variable xn is equal to small xn. In a case when all these random variables are discrete, can be found using its PMF function. Let's call it f subscript names of your random variables at x1, x2, and so on, xn. In a case when our random variables are continuous, then we are going to use PDF, multivariate PDF, and we'll have to integrate it In the case when we're working with a single random variable, we were looking for a probability that this random variable lies on some interval on a line. In the case, in a bivariate case, we were looking for a probability that our random variables, let's call them x and y, they lie in some region on an xy plane. Now, in a multivariate case, we'll be looking for a probability that our random variables x1 through xn lie in some region of n space. All right, and then it can be found by integrating its multivariate PDF. We'll have n integrals here over the region R of our multivariate PDF. dx1, dx2, and so on for each of these integrals, dxn. Multivariate PDF then defines probability. So big F of subscript x1, x2 through xn at the point x1 through xn defines probability that first random variable is less or equal than x1, second random variable is less or equal than x2, and so on. Last random variable is less or equal than xn. And in a case when these random variables are continuous, then we can derive multivariate PDFs from multivariate CDF by taking n's partial derivative. And so by taking n's partial derivative of CDF function. And finally, marginal PDFs in the multivariate case are defined as follows. So for instance, let's consider the case for when we are working with continuous random variables. In that case, we'll be working with integrals, and similarly in a case when we have n discrete random variables, we'll be working with sums. So let's show that for continuous and for discrete random variables, it's similar. All right, so we have n random variables. Then we can find marginal PDF of any subset of those n random variables. So let's assume that you have n random variables, and now you are interested, let's say, in a subset of those n random variables. Let's call them xi's, xi1, xi2, xir. And let's assume you are interested in this subset. So basically, our list of random variables is divided into two subsets, and we'll call the left random variables as xj's, xj1, xj2, up to xj n minus r, since in total, the number of random variables we have in both of the subsets should be equal to n, right? Now, if we are looking for marginal PDF of a first subset, xi's, then we have to Then we have to integrate overall those random variables xj's. So from minus infinity to infinity. So here we'll have n minus r integrals. Joint PDF of those n random variables. Dxj1, Dxj2, and so on, Dxj n minus r. Okay, now one last point here. Every time we were listing all of our random variables, now for convenience, guys, instead of listing all these random variables every time, you can use the vector notation. So for instance, if you are interested in, let's say, multivariate CDF of these random variables, then you can simply call this as f subscript big X. So that should be in bold. So this is a vector. And that is also a vector that is going to contain values for x1 through xn. Independence of two random variables. We have a very similar definition for independence of two random variables to the independence of two events. If you recall, we call events A and B independent if probability of their intersection is equal to the product of their individual probabilities. Now, if we have two random variables, we call them independent if for every interval A and interval B, probability that X lies in A and Y is in interval B is equal to the product of these individual probabilities, probability that X is in A multiplied by probability that Y is in B. Now we have the following nice property to quickly determine whether two continuous random variables are independent or not. Let's assume that we have continuous random variables x and y. Let x and y be continuous random variables. And also suppose that region R so region R here represents values of x, y such that their joint PDF is non-zero. Suppose that region where their joint PDF is non-zero is a box, is a rectangular box. Possibly unbounded. So we can have a case when our joint PDF is non-zero over all xy plane for all values of x from minus infinity to plus infinity and y from minus infinity to plus infinity. Is a rectangular box, possibly unbounded, with sides, if any, parallel to the coordinate axis. Then random variables x and y are independent if and only if their joint PDF can be expressed in the following form. As a product of functions h and g, such that h is a function of only x and g is a function of only y. For all values of x and y in that region R. And if that's the case, then we can find a constant k such that the marginal PDF of x is equal to k h of x, and then marginal PDF of y is 1 over k g of y. Right, so let's split this part for a second. Now let's come back to our theorem here. Why do we need this stuff about region where joint PDF is non-zero? You will see why we need this part here in a second. So let's go over the theorem again. Let x and y be continuous random variables, and let's suppose that region R here, where joint PDF is non-negative for x and y, represent a rectangular box with sides that are parallel to the coordinate axis. Then x and y are independent if and only if their joint PDF can be represented as follows. As a product of functions h and g, where h is a function of only x and g is a function of only y. And then if that holds true, then we can find their marginals from these functions h and g. Now let's take a look at the following problem. Suppose that we have two random variables x and y. Their joint PDF is given as follows. Are x and y independent? And if they are, let's find their marginals. So first, let's check our condition for the region where their joint PDF is non-zero. So we can see that it represents as a square from 0 to 1. So we are fine with that. Now, let's pay attention to our joint PDF here. We can see that it can be represented in the following form. H of x is equal to 12x and g of y equal to y 1 minus y. So we can see that we can easily split up x and y's, and f of xy can be represented in this form here. So x and y are independent. Now let's find their marginals. So we have to multiply h by some constant k and g by some constant 1 over k, such that those two are going to be valid PDFs. So let's find first integral of h of x over all values of x from 0 to 1. That will be 12x squared over 2, so 6x from 0 to 1, so it's equal to 6. Then for to make a valid PDF with h of x, we need to multiply it by 1/6. So marginal PDF of x is then given as 2x. And then we have to multiply g of y by, if this is our k, if our k is equal to 1/6, then we have to multiply g of y by k. So marginal PDF of y is then given as 6y 1 minus y. All right. So if we come back to our theorem here, so we have to find such k for h, h was 1/6. Then we have to multiply by 1/k our g of y. All right. Now that was a nice case when boundaries where our joint PDF is non-zero was a square. Now let's take a look at another problem. Let's assume that our PDF for x and y is defined as follows. Is of the form k x squared y squared when x squared plus y squared is equal is less or equal than 1, and it's 0 outside of here. Okay, now we can see that we can split joint PDF into functions. Let's say g of y is equal to y squared and h of x equal to kx squared. However, if we conclude from here that x and y are independent, then we would be wrong, since we didn't pay attention at the boundaries of the region where joint PDF is non-zero. So here, boundaries here represent as a circle, a unit circle with the center at 0. And in our theorem here, we had the condition that the boundaries, sides or boundaries of our R, of our region where joint PDF is non-zero, should be parallel to the coordinate axis, which is not true here. So let's show why x and y are dependent here. Now, x and y are dependent. Let's show why this is true. When y is equal to 0, x squared lying in interval from -1 to 1, or x squared being less or equal than 1, and x being in interval from -1 to 1, are going to produce some non-zero probabilities. So probabilities that x squared is less or equal than 1 will be something non-zero. If y is equal to, let's say, 1/2, then only values of x squared less or equal than, if we substitute 1/2 here, only values of x squared less or equal than 3/4 are going to give us non-zero probabilities. So what happened here is that knowledge on random variable y had an effect on probabilities related with second random variable x, which means that x and y are dependent. Again, the reason for that is even if we can represent our joint PDF in this form here, the boundaries of region where joint PDF is non-zero, here we have a curved boundary, and we need a rectangular boundary with sides that are parallel to coordinate axis. Even so, in any case, when you will have a curved boundary, or even if you will have rectangular boundary but with its sides being not parallel to your coordinate axis, then your random variables are going to be dependent. Finally, we are going to conclude our section on joint densities with the following definition on random sample. Let's assume we have a list of random variables x, y through xn, and these are independent random variables, and they all follow the same PDF. Then x1 through xn are said to be a random sample of size n. Another definition for this random vector here is IID. So we call these random variables IIDs for independent. Second I stands for identically, and D stands for distributed. So they are independent and identically distributed, since so they follow the same PDF. This concludes our section on joint densities.